Good morning, everybody. We're going to talk about Hess's law today. It's another way for us to find delta H, or the enthalpy. And I know it looks funny to see how Hess's law is spelled. There's two different ways: Hess's with an apostrophe S, or Hess with just an apostrophe. So that's the way it is. Okay, Hess's law in scientific speak. Don't write this down because it's technical. The delta H for a reaction is equal to the sum, add them all up, of the delta H values of any reactions that, when combined, equal the overall reaction. So what are we really meaning here? Reactions are similar to algebraic equations, and they can be combined into one large reaction. When this happens, adding the delta H values for the other equations equals the delta H of the combined equation. Let's try an example. So imagine these two equations. We have the first equation here, and the delta H is a negative 75 kilojoules. Okay, the second equation happens, and the delta H is a negative 82 kilojoules. When combined, if you put both of these reactions together, spend a moment and look at it. So here's the BaO, there's BaO. There are two SO3s, one in each equation. So notice that the coefficient became 2SO3. There's one water, and then what we get as products are the two added together. And so if you add the delta H's up, you find out that that combined reaction at the bottom equals a negative 157 kilojoules. It's pretty cool that this works. So what's the big deal? Why would we combine these? Well, combining them for the sake of combining them is pointless. We're using Hess's law to do equations that we can't do for some reason in the laboratory. Maybe our school laboratory, or maybe in a big fancy laboratory, they can't do the reaction. So they're going to add up the reactions that they can do in order to figure out what that reaction would be. Okay, so let's try again. Let's combine these two reactions to get the reaction that's on the bottom. So what I notice is that there is an SO3 here and an SO3 here, but there's no SO3 there. How did that happen? So it says the original equations can be manipulated in three major ways. You can multiply them, you can divide them, and you can flip them. What? Flip them? You can reverse the reaction. When the equation is manipulated, the delta H value must be manipulated as well. So if you're going to multiply a reaction by 2, then you have to multiply your delta H for that reaction also by 2. So, and then dividing and or changing the sign. If you're going to flip the reaction around from the products are now the reactants, and the reactants are now the products, you have to change the delta H's sign. So if it was negative, you make it positive. If it was positive, you make it negative. So let's go back to our example number 2. You noticed in our target equation that there was no SO3. Well, what if we reverse equation 1? Watch it again. So here is equation 1 initially. If we added these two equations, we would have 2 SO3s, but that wasn't in our target equation. But what if we flip equation 1, and so now SO3 is on the other side? It turns out that these two, when it's a reactant and a product, they cancel each other. Now we're left in front of the arrow with an H2SO4, and in front of the arrow BaO, and to the right of the arrow no SO3, they canceled out, a water and a BaSO4. Now if we're going to reverse, remember, take a look at what happens to the delta H. It went from a negative 75 to a positive 75. So when we combine these two reactions, the sulfur trioxides, I have to think about that for a second, cancel each other out. And we end up with the correct equation. And then you add up the two delta H's to get a minus 7 kilojoules for that particular reaction. Okay, let's try another example. We've got 3 equations, and we need to get down to this target equation. That's what we're always going to call it, the target equation. Right now, I see that in front of the arrow, we have an O2, but down here, there's no O2. So I know I'm going to have to flip something. I know I'm going to have to get rid of something. I see that I have 2 carbons, and I have 1 carbon up here, but I have 2 carbons down there. So not only am I going to need to flip some things around, I'm probably going to need to multiply some things. So let's go ahead and see what we can do to play around with it. So for the first equation, we're going to go ahead and multiply it by 2. So what we end up with is 2C, 2O2, 2CO2. We multiplied the entire equation by 2. So all we're doing is increasing the coefficients that are in front. We don't change any of the subscripts. Okay, so then for the second equation, we're going to multiply that one by 3. Now watch what happens, because this one's a little bit awkward. We get 3H2, but notice that the O2 was a 1/2. So now it becomes 3/2 O2. And the reason it's 1/2, it's a way of writing an O all by itself that doesn't occur in nature. Anyway, just trust me on that. And then for the last equation, we have to do 2 things. We have to flip it around to get rid of the oxygens because they didn't belong there. And we have to divide it by 2. So let's see what that does when we flip it around and we divide it by 2. Look at this. Now we have 7.5 O2 on the right side of the arrow, and we have, what would that be? 7/2 O2 on the left side of the arrow. They cancel each other out. So let's watch this a little bit more carefully here. So if you look at this, the carbons are left. You have 2 carbons, so that's remaining. Everything in green is remaining, and that's our target equation. Notice that the 2O2, so this was originally, this one right here was 2O2. That's the same as, this will help you, that's the same as 4/2 O2. And if you add that to 3/2 O2, that's 7/2 O2. And that's what we had down in this other reaction. And the third reaction was 7/2 O2. So they canceled each other out. We had 2 CO2 on the right side of the arrow. We have 2 CO2 on the left side of the arrow. We have 3 H2O on the right side and 3 H2O on the left side. So all that's remaining are the ones that are circled in green. These 2 are in front of the arrow, and this one is behind the arrow. So that's our target equation. Now we have to add up all of the delta H's. So for the first equation, we multiplied it by 2. For the second equation, we multiplied it by 3. And for the third equation, we divided it by 2 and we flipped, which means we have to change the sign. So notice that it was a negative 3,000 some. Now we're going to divide it by 2, so it'll be negative 1,500. But then because we flipped it, it becomes a positive 1,500 some. So now we add them all up and we find out that that target equation has a delta H of negative 84.6 kilojoules. Pretty cool. Let's try one more as an example. So we've got 3 equations. Why don't you pause my video to see if you can figure it out? I'll give you a moment to pause it. Okay, I'm going to keep going with the solution here. So there's our equation that our target equation down at the bottom that we're trying to get. Things that I am noticing, we have 1/2 O2 here, but I have 3/2 O2, I have a 1 O2, and I have a 1/2 O2. So some of those are going to have to cancel out for me to end up with just 1/2 O2 on the right side. I have carbon dioxide and carbon dioxide on the right side of the arrow, but there's no carbon dioxide here. So that tells me one of these is going to flip. Ruh-roh. Okay, so let's take a look. We're going to flip the first equation. So now the CO2 is on the front. We're going to leave the second equation alone. And then the third equation, we're going to, that's covered up. We're going to multiply that second equation by 2. So let's take a look and see if we can figure out. If we flip the CO2, so the CO2 is now in front of the arrow. There's a CO2 behind the arrow. They cancel each other out. We see here that we multiplied by 2. Here's a 2H2 in front of the arrow, and that one stays as is. So there's going to be a 2H2 in front of the arrow. Those are just some examples. All right, so let's go ahead and take a look. And nothing's happening for some reason. There we go. Okay, so now we have to adjust our delta H values. We flipped the first one, so we make that a positive. We leave the second equation as is, so it stays the same. And then the last equation, we multiplied it by 2, so it stays a big negative number. When you add them all up together, you have negative 238.7 kilojoules. All right, we have a Hess's Law worksheet. There is an answer key posted, and there are more practice problems at this link if you need anything. Let me know if you have any questions. Have a great day. Bye-bye.